This lecture is about electric field lines, which are just a useful way to visualize electric fields. Now, we've already talked about the two simplest cases, that is the case of a single point positive charge or a single point negative charge. But what happens in between these? In order to think about that, we'll consider what the electric field is on a center line that bisects the two charges. First, we'll consider the electric field at a point exactly in the middle of the two charges. Now, in order to think about that, we'll imagine a test charge, a positive test charge at that point, and we'll ask, okay, what would be the force on this positive test charge? Well, there will be a repulsive rightward force due to the positive charge to the left, and an attractive rightward force due to the negative charge on the right. So the force on a positive test charge is to the right, and by the definition of electric field, it points in the direction of the force on a positive test charge. So since the force on a positive test charge is to the right, the electric field there in the middle is to the right. Now let's consider a positive test charge on this bisecting line, but a little bit up above the center. It will feel a repulsive force from the positive charge on the left, as well as an attractive force from the negative charge on the right. Now these two forces will be equal. How do I know that? Because they're an equal distance from the two charges, and the two charges themselves are equal and opposite. I forgot to mention that earlier. I should have. This one is some charge plus q, and this is some charge that is minus q. Opposite sign but equal size. So the size of these two forces is the same. It's just the direction that's different. Now their direction, one is above the horizontal and one is below the horizontal by the same angle. So this means that their vertical components will be equal and opposite, and they'll exactly cancel. But their horizontal components are in the same direction, so they'll add to each other, resulting in a net rightward force on this positive test charge. By a similar geometric argument, a positive test charge down here has a net rightward force. And this gives us a sense of what the electric field lines look like in between these two charges, and that helps us to start to fill it in. Now from this little example, we can see examples of a few rules about electric field lines that will help us both in drawing them and in interpreting them. First, electric field lines, they all start at positive charges and end at negative charges. Except at a positive and negative charge, they don't start or end. So all these electric field lines, they may go off screen, but they all come back on screen, and they end at the negative charge. When the electric field lines are closer together, the electric field is stronger. So note, close to these point charges where the electric field will be strongest, that's where the field lines are closest together. Far away from the electric charges, the field is weakest, and that's where the field lines are farther apart. So close together field lines means stronger electric field. And finally, electric field lines do not cross. Now there's a nice way to understand why electric field lines cannot cross. Suppose we have two electric field lines that cross. What would be the electric force on a positive test charge there? Would it be this way, or would it be this way? These two electric field lines are giving contradicting information about what the force on a positive test charge is there. It doesn't make sense, it's ambiguous. So that's why electric field lines cannot cross. So these four rules will help both in drawing electric field line diagrams and in interpreting them. Electric field lines start at positive charges and end at negative charges. Where they're closer together, that's where the electric field is strongest, and electric field lines do not cross. Let's do some practice interpreting or drawing electric field diagrams. Think of this as an example problem. We just did the diagram for a positive and a negative charge. Now let's do one for two positive charges. We know what the electric field looks like close to a positive charge, but how about in the space in between? Well, we can't just extend these, because that would result in them crossing, and we know that's not allowed. So these must bend away from each other. Following this pattern and filling the rest in, we get something like this. Remember that an electric field line can only end at a negative charge, so all of these electric field lines must just go off screen. Now, what does this actually tell us about the electric field along, say, the center line? Let's get some practice interpreting this diagram. Well, along the center line, the electric field is going to be up. We can see from the direction of these arrows. And it's going to be strongest here where the electric field lines are closest. So further down, where the electric field lines are farther apart, the electric field itself is going to be a little bit weaker. Down here, similarly, points downward, strongest here where the field lines are closest together, and then not quite so strong. Now, as it goes from upward and strong to weaker, 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 and then flips to downward, there's got to be a point right here in the middle where the electric field is actually zero. Now, these conclusions are consistent with the conclusions we would get if we think about the forces on a positive test charge. Okay, a positive test charge up here is going to have a repulsive force in that direction from the charge on the right, and another repulsive force in this direction from the charge on the left. The horizontal components of these repulsive forces cancel, while the vertical components will add together, resulting in a vertical net force, so the electric field there must be upward. Exact same story down here at the bottom. Now what about the very middle? A positive test charge here will have a repulsive force pointing to the right due to the charge on the left, and a repulsive force pointing to the left due to the charge on the right. Those forces are equal and opposite, so they'll exactly cancel. So the force on a positive test charge right at the middle is zero, so the electric field is zero, just what we had concluded from the electric field diagram that we drew. Let's do another example. Let's consider two parallel plates, one positively charged and one equally and oppositely charged. The plates will have, these charges are uniformly distributed across the plates. So what's the electric field going to look like in between them? Well, we know the electric field lines must start at positive charges and end at negative charges. And they kind of have to go straight across, because if they don't, they'll wind up crossing each other. Now out here on the ends, they've got room to bow out a little bit without crossing any neighboring electric field lines, so they can spread out a little bit out here. For now, we're just worrying about what's going on in between these parallel plates. So, what we can learn from interpreting this is that, first of all, the electric field is, of course, pointing to the right from the positive plate to the negative plate directly. It's not pointing at any angles, because if it would, these electric field lines would wind up having to cross each other somehow. And second of all, the strength of the electric field is uniform, because the spacing between the electric field lines stays the same. So the electric field line is the same really close to the positive plate as it is really close to the negative plate. And that's a useful piece of information we can learn just from interpreting this electric field line diagram, because the field lines are spaced equally. This charge configuration is called a parallel plate capacitor, and we'll talk about it more when we learn about electrical components such as capacitors and in particular parallel plate capacitors. Let's do some homework problems. This is homework problem 3 for this week, because if I recall correctly, we had 2 in the previous lecture. Draw the electric field lines for this configuration of 4-point charges, 2 positive arranged on opposite corners of a rectangle and 2 negative arranged on the other 2 opposite corners of a rectangle. For problem 4, draw the electric field lines for this configuration. A plate of positive charge distributed evenly throughout, next to its small tight little ball of negative electric charge. Now let's do an example where we actually compute an electric field. We'll consider a configuration of two equal positive charges, both with charge 10 to the minus 8 coulomb, some distance L equals 1 meter apart, and we'll consider the electric field at three locations, A, B, and C. First, we'll compute the electric field at location A. Now we're going to make use of the equation we derived in the first lecture for the electric field due to a point charge. It's kq over r squared. Now applied to point A, there's going to be a repulsive electric field due to the charge on the left, and another repulsive electric field due to the charge on the right, which is a longer distance 3L over 4 away. Because this repulsive electric field points in the opposite direction to the left, we'll give it a minus sign. With some algebra, we find that the result is 1,280 newtons per coulomb. Now that's at location A. How about location B? Well, location B, because it's right in the middle, half the distance, it's going to get an equal and opposite repulsive electric field from the charges on the left and the right. They'll exactly cancel, so we know right away that the electric field there is 0. As for location C, the situation is symmetric. It's exactly the same as the electric field was at location A, except now it's going to be in the opposite direction. It's going to be to the left. So we get minus 1,280 newtons per coulomb. Now we'll do another homework problem. This is homework problem number 5 if I haven't lost count, and it's exactly the same as the example problem we just did, except now one of the charges is going to be negative 10 to the minus 8 coulombs. We now turn to the topic of electric dipoles. Electric dipoles come up for a number of situations. One is that a lot of molecules just are polar molecules. They are electric dipoles. So what an electric dipole is it's effectively a positive charge and a negative charge separated, equal and opposite charges separated by some small distance. Now, some molecules behave like this. They're called polar molecules, and one example is water. In water molecule, where the oxygen atom is somewhat more negative, and where the hydrogen atoms are somewhat more positive, resulting overall in just a more negative charge up here and more positive charge down here. From a distance, that looks like a plus charge and a minus charge separated by a very small distance. Another way in which this comes up comes from the fact that atoms are essentially a positively charged nucleus surrounded by a tightly bound, orbiting, negatively charged electron cloud. If we apply, say, a downward E field, the result is that this pushes the nucleus downward and pulls that electron cloud upward, resulting in more of the positive charge being below this line and more of the negative charge being above it. Essentially you have the same situation, a very small positive charge and a very small negative charge that's very close to each other. Note that in all of these examples, the dipole has a net neutral charge. Okay, this is not an ion, it's just a neutral atom. This is just a neutral atom. The water molecule overall is neutral. So all of these can be modeled by equal and opposite charges a very small distance apart from each other. Now we know what the electric field lines look like more or less. What we'll do now is actually calculate the electric field due to an electric dipole. And we'll do an example of calculating the electric field up here directly above this electric dipole. And then I'll give you the homework problem of finding out the electric field next to it along this line that bisects the two charges. By the way, I think I forgot to mention here that when you have this situation where an applied electric field turns atoms into tiny little dipoles. This is called an induced dipole. So let's start with our example problem of considering an electric dipole, and we want to know what the electric field is due to this dipole some distance above it in the direction of the positive part of that electric dipole. The two charges in the dipole are equal and opposite. We'll call them plus q and minus q. The distance between them, we'll call that d, and the distance we are away from the dipole, we'll call that r. Now remember, dipoles are small, okay? They're atoms and molecules typically, and we're much farther away from it. So d is very, very small compared to r. We're going to use that to make an approximation. So in the electric field, we have one term coming from the positive charge on top, and another term coming from the negative charge on the bottom. The negative charge is just a little bit far away, a distance r plus d rather than just r. So let's do some algebra. Now, at this point, we should remember that d is much, much smaller than r. So here we can have, where we have 2dr and d squared, we can drop the d squared, because you take a small number, you square it, you get really, really ridiculously small. D is much smaller than r, so d squared is going to be much smaller than 2d times r. So we can drop this whole d squared on top. On the bottom, similarly, we can drop really all the terms with d, because this r to the fourth is going to be much bigger. When you've got a big term added to something much smaller, we're dropping the small thing and just keeping the big one. It's a good approximation. The result then is that the electric field is 2kqd over r cubed. Now, this quantity qd is often just called P, or defined as P, where this quantity P is the dipole moment or electric dipole moment. The result for the electric field then just simplifies to 2kp over r cubed, and this is going to be upward, which we could see from the previous drawing where we had drawn the electric field line. It's pointing upward. A couple of useful things to note. First of all, greater the dipole moment, the greater the electric field. Now that can happen by making d bigger or by making the charge bigger. Either one will make the dipole moment bigger and will make the electric field bigger in proportion. Note also that unlike the electric field due to a point charge, which goes like 1 over r squared, the electric field due to a dipole goes like 1 over r cubed. Finally, it's useful to take a look at units. Remember that the electric field due to a point charge was kq over r squared, and that had the proper units of electric field. But here we've got kq d over r cubed, so we have an extra unit of distance on the bottom from the r cubed rather than r squared, but we also have an extra unit of distance on the top from this d, which is just the distance between the two charges in the dipole. So we get an extra unit of distance on top and an extra unit of distance on the bottom, then they cancel out and don't change the units overall. So the units work out for this 2kp over r cubed quantity. Okay, so for your homework problem number 6, you'll compute the electric field for the same dipole, but now at a different location rather than up above it in the direction of the positive charge, right out to the side, some distance r horizontally away from it. Okay, and you're right on the center line. You're right on the center line between you're right on the line that bisects these two charges. We'll make this one multiple choice, so 4 possible answers: kp over r to the fourth, kp over r cubed, 2kp over r to the fourth, or 2kp over r cubed. See if you can identify which one of those is the right answer and why. We'll do another example now. We have a uniform electric field pointing to the right, and immersed in it is an electric dipole. What is the torque exerted on this electric dipole by the electric field? Well, first of all, on this positive charge, there's going to be a rightward electric force. On the negative charge, a leftward electric force. So we can already start to see how this dipole is going to want to rotate this way about an axis at its center. But what is the actual torque? Well, torque is equal to, remember, it's the perpendicular component of a force times the distance from the axis of rotation. Now the perpendicular component is this one, because it's perpendicular to a vector from the axis of rotation to the point of the positive charge. Okay, so what is this perpendicular component? Well, some geometry will show us that this angle here is theta, and so that makes that perpendicular component basically be F sine theta. Substituting that into the torque, we have Fr sine theta. Now note that the force itself, remember just from the definition of the electric field, is the electric charge times the strength of the electric field. And in this case, the radius is 1/2 the dipole separation d. So we get R is just d over 2. Now note that this was just the torque on the positive charge. There's going to be an equal and opposite torque from the negative charge. So the net torque then, I'll switch my color back to black. The net torque, the sum of the two torques, is going to be the combination of these two. So 2 times QE d over 2 sine theta. The 2's cancel. Now recall that Q times D is equal to called the dipole moment. It's equal to P, and the answer is just E times P sine theta. Now I just realized that a few seconds ago I said that the negative charge gets an equal and opposite torque. That's not right. It gets an equal torque, so that they don't cancel out. The two torques add to each other, and that's why we got this too. Okay, for your last homework problem, problem number 7. Suppose we have two electric dipoles. Let's call one of them P1 and one of them P2. Note that they're oriented differently. They both have the same dipole strength. We'll just call that P. What is the torque exerted on this dipole here, P1, by the dipole P2? Let's put them some distance r apart. Dipole strength is just P. So what is the torque exerted on this one in terms of R and P?